Hello everyone. In this video, I am going to start power system stability. Different contents of power system stability are, first of all, we will see what is a power system stability, what is the importance of power system stability. When we are speaking about stability, we should know what is meant by instability and what causes the instability. So we will be seeing what is a disturbance, what are types of disturbances, then what is stability and types of stability. Then we are designing a model of a synchronous machine. Actually, whenever we are speaking about stability, we will be speaking about different components connected to power system. Different components for connected to power system means many synchronous motors and synchronous generators are connected in parallel to provide the demand to the grid. They are connected in synchronism. We already know what is meant by synchronism. They are connected to grid. Whenever there is small disturbance or large disturbance in that synchronous generator, what will happen? The ability to attain the synchronism, they should not lose the synchronism. That is only we will be telling the power system stability. So we will be designing a synchronous machine model for stability analysis. And what are the methods of improving steady state stability limit? Then what is power angle equation and power angle curve? Then dynamics of synchronous machine, that is swing equation and swing curve. Then problems on swing equation. Actually, steady state analysis and transient analysis are the two types of stability analysis. Steady state analysis is said for small disturbance. Transient analysis is said for large disturbance. So steady state analysis. First, we will see about steady state analysis in the first 4 videos. Then last 4 videos, we will be seeing about transient analysis. So after seeing problems on swing equation, we will see what is the steady state stability for small disturbance, how the steady state stability will be analyzed using swing equation. Coming to transient stability, we will see what are the assumptions. And when we come to analysis of transient stability, we will be using equal area criteria and solution of swing equation by step-by-step method, modified Euler method, and Runge-Kutta method. Let us move on to the introduction. A large power system consists of, as I said, a large power system consists of many number of synchronous machines or equipments or components operating in synchronism. Whenever we connect many synchronous machines in parallel to operate, to provide certain load, we will be, whenever we are adding a synchronous machine to the grid, we will be checking the conditions to be satisfied so that it will be in synchronism. We will see the synchronism concept in induction and synchronous machines. When the system is subjected to some form of disturbance, there is a tendency of system to develop force to bring it to the normal or stable condition. The term stability refers to stable operation of synchronous machines connected to power system when they are subjected to sudden disturbances. Depending on the nature and magnitude of disturbances, the steady state studies can be classified, stability studies can be classified into steady state stability and transient stability. Steady state stability. It is the ability of power system to remain stable. That is, without losing the synchronism for small disturbances. Static stability. In steady state stability, we had two types. Static stability, as I had shown here. This is the steady state stability. It is classified into static stability and dynamic stability. And another classification is transient stability. The steady state stability is actually the ability of the power system to remain stable without losing synchronism for small disturbances. Static stability refers to inherent stability that prevails without the aid of automatic controlled devices, whereas dynamic stability refers to artificial stability given to an inherently unstable system by automatic controlled devices. In static stability, it is the inherent stability, it is the inbuilt stability of the power system where we won't use any automatic control devices. Whereas in dynamic stability, we will be using inherently externally artificial. It is an artificial stability given to an unstable system by automatic control devices. Transient stability is defined as the stability of power system to remain stable for large disturbances. Large disturbances mean change in load, loss of generations, excitations, transmission facilities, switching operations, and faults. Importance of power system stability. What is the importance? Generators must be kept in synchronism always. If there is relative motion between begins to change too much, relative motion, then what will happen? Uncontrollable oscillations will appear in the grid, which cause damage to the generator and to the equipment connected to the grid. Relays are used to detect this condition and trip the generators before the damage occurs. Tripping prevents the damage, but it results in under frequency and possibly load interruption. And in worst case, cascading outages and blackouts will come. These blackout concepts you will understand in power system protection techniques. Then, what is a disturbance in power system? A disturbance is a sudden change or sequence of changes in one or more parameters of the system or in one or more operating quantities. Types of disturbances, we have small disturbance and large disturbance. As I said, steady state stability deals with small disturbances, transient stability deals with large disturbances. Coming to small disturbance, it is a disturbance for which the equations that describe the dynamics of the power system may be linearized for the purpose of accurate analysis. That means it can be linearized. Small disturbances can be linearized to get accurate analysis. Then large disturbance. It is a disturbance for which the equations that describes the dynamics of the power system cannot be linearized for the purpose of accurate analysis. Accurate analysis. Coming to synchronous machine for stability analysis. Normally, a synchronous generator can be considered. Here we are considering the classical model of a synchronous generator, that is this diagram, where the saliency is ignored for steady state analysis. Now in this diagram, we had a voltage source and we had a reactance. Now here Vg is the node. This node Vg, generator terminal voltage, can be eliminated by converting this total star to delta. So I am converting the star to this delta. So when I convert the star to delta, actually when we are converting star to delta, here what is there? Here we had Zs and Zl. So first we need to convert star to delta in impedance. Then you can invert that impedance to get the admittance. Actually, first we are converting this. Here what we will get? Z10 we will get. Since we had Zs, Zl and Jxd, these three are impedances. First we need to convert the star to delta in Z. This is Z12 and this is Z20. Now we know when we are converting star to delta, what will happen? This Z10, that is, suppose we had a star like this and we are converting this into delta. I take here it as A. This is B and this is C. Then this line is AB of this delta, BC and AC. Now, when AB will be is equal to A plus B plus AB by C. So what it will happen? AB is equal to star to delta transformation. Formula for AB is equal to A plus B plus AB by C. So what it will happen? It will be, if you take LCM, you will get AC plus BC plus AB by C. This is what is this? This is the impedance ZAB. Now, if you want YAB, you should invert it. So what you will get if you want YAB? C by AC plus BC plus AB. The same thing. See, Z10 is coming here. So it is JXD plus JXD dash plus XS plus JXD dash XS by JXD dash ZS by ZL. When we take LCM, Z10 will become JXD dash ZL, JXD dash ZS plus ZL ZS by ZL. If you invert that, we will get Y10. So using this concept, you can find all these three things. So now I will be getting like this. Since these both are grounded, I am separating this ground thing separately. Now, here at the E dash, current entering is I1 and at V, current entering is I2. If I apply nodal analysis, I1 is equal to what I will get? Y10 plus Y12 E dash minus Y12 V. Similarly, I2 is equal to minus Y12 E dash plus Y20 plus Y12 V. This is Y10 actually. This is Y10. Why? Because if you see I1 is equals to sum of this current plus sum of this current. What is this current? Voltage into V. See, since here it is ground at 0, I1 is equal to E dash minus 0 into Y10 plus E dash minus V into Y12. If I take common, then I will be getting this equation. Similarly, I2 is entering here and V is voltage here. Here it is 0. So this I2 will be is equal to sum of this current and sum of this current. So I2 is equal to V minus 0 into what is this? This is Y20 actually. V into Y20 plus V minus E dash into Y12. If I solve, I will be getting this equation. Then I got this matrix. I am writing that equations. We know Y10 plus Y12 is capital Y11. We already studied Y bus. So you know this. And minus Y12 is actually capital Y12. Similarly, minus Y12 can be capital Y21. And Y20 plus Y12 is capital Y22. So I am writing this in the form of a matrix. So I get this. Now, if I take, this is the matrix, I am considering V as E2 dash. Now I1 is equal to E1 dash into Y11 plus E2 dash into Y22. Now what I will get? I know that S is equals to P plus JQ. which is equals to V into I conjugate. Normally, complex power is equal to V into I conjugate. Since I had taken S1, it will be equal to E1 dash into I1 conjugate. What is E1 dash? E1 dash can be written as magnitude of E1 dash at an angle of del 1. You already know that voltage corresponding angle will be represented by del, and the admittance elements corresponding angle will be represented by theta. We had seen this in Newton-Raphson and the fast decoupled methods. So since E1 is the voltage, corresponding angle, it is del 1. Now into I1 conjugate. What is I1? Just now we had got what is I1 here. So E1 dash at an angle of del 1, Y11 at an angle of theta 11 plus Y22 at an angle of, sorry, you can, here it is Y12. Y12 at an angle of theta 12 into E2 dash at an angle of del 2 whole conjugate. We know that whenever we had a conjugate, if A plus JB, that is rectangular form, had a conjugate, then we will be getting A minus JB. A plus JB whole conjugate will give you A minus JB. When we had, this is actually rectangular form. When we had in polar form, that is, suppose A at an angle of B, when we are taking this conjugate of this complex member in polar form, we will be getting A at an angle of minus B. So what will happen when I keep conjugate of this? Here we had a conjugate. So what will happen? All this del 1 will become minus del 1. Here, this del 1, okay, this del 1 is becoming minus del 1. And this theta 11 will become minus theta 11. Similarly, this theta 22 will become minus theta 22. And this del 2 will become minus del 2. Now I am multiplying this with this. What I will get? E1 dash square. E1 dash square. Then E1 dash. Okay. E1 dash square into Y11. This magnitude terms. This is the magnitude term. And this is the magnitude term. And this is the magnitude term. I am taking all the magnitude terms. So I will get, this is the whole magnitude term at an angle of, see this plus del 1 minus del 1 will get cancelled. So only this minus theta 11 will left. So E1 dash square into Y11 at an angle of minus theta 11 will be coming. Then multiplying this term with this, that came. Now we will multiply this term with this. What we will get? E1 dash into E2 dash into Y12 del 1 minus del 2 minus theta 12. That is what I had written here. Now we know that normally Z is equals to what we will write. Real part of impedance is R plus JX. That is resistance plus reactance. Similarly, when we had an admittance Y will be written as, Y is the inverse of Z. So Y can be written as real part of Y is inverse of resistance, that is conductance G plus J, inverse of X, that is inverse of reactance is susceptance B. So Y can be written as G plus JB when we are converting it from polar form to rectangular form. See, this is actually polar form. Now I am converting this polar form into rectangular form. When I am converting this polar form into rectangular form, since we had admittance here, as I said, the admittance can be written like this. So Y11 real part is G11 and imaginary part is B11. Since there is a negative sign in front of theta, this minus will. This is actually rectangular form. Now, if you see what is there, I am considering this del 1 minus del 2 as del, and theta 1 2 is equals to gamma plus pi by 2. What I will get? Gamma del minus gamma minus pi by 2 I will get. See here, I converted this y11 at an angle of minus theta 112 rectangular form. I got this. So what I am writing? E1 dash square into G11 minus JB11 plus E1 dash E2 dash Y12 at an angle of del minus gamma minus pi by 2. Now this total I am converting into, actually whenever we had an angle, what can we do? This angle can be converted. This angle can be converted. Here we had converted the whole thing into complex form from polar to rectangular. But here we can write this angle as cos theta plus j sin theta. So I am converting angle alone from polar form to rectangular form. So I will get E1 dash E2 dash Y12 cos del minus gamma minus pi by 2 plus j sin del minus gamma minus pi by 2. I converted this angle from polar form to rectangular form. So I got this equation. Now from this equation, see here P is the real part on the left hand side. And here what we had real part, this is a real term. There is no j term. Since we had j term here, this is not. And this is a real part. I am equating this P in the left hand side. Real parts of left hand side and right hand side I am equating. So what I will get? P1 is equals to E1 square G11 plus E1 dash E2 dash Y12 cos of del minus gamma minus pi by 2. Cos theta minus pi by 2 can be written as sin theta. So actually, yeah, cos theta minus pi by 2 can be written as sin theta. This sin theta is actually cos del minus gamma minus pi by 2. Now, this term I am taking as PC and this, okay. Now, if you see this circuit in the previous slide, here we had ZL, ZS and JXD dash. So the circuit is almost, network is purely reactive. When the network is purely reactive, what is meant by reactive? Reactive means X. That means network is purely reactive means R is equals to 0. When R is equal to 0, what is the inverse of R? G. So G will be neglected. Why? Because when we have only reactive term, its corresponding inverse B will be present in the admittance and G is neglected. So what will happen? In this total, this term will become 0. This term will be 0 and only this term will be left. So PE is equals to E1 dash E2 dash Y12 sin del minus alpha. Del minus gamma. So now here this, when this del minus gamma is equals to pi by 2, you will be getting maximum value. That is del minus, when del minus gamma. Why? Because sine will get its maximum when theta is equals to 90. So when del minus gamma is equals to pi by 2, you will get the P max is equals to E1 dash E2 dash Y12. Y12 can be written as 1 by Z12. Why? Because 1 by X12. Why? Because as we had said, the resistance is negligible. Y is equals to 1 by Z. Z is equals to R plus JX. R is negligible. So X1. So G11 is equals to 0. So PC is equals to 0. And theta 12 is equals to pi by 2. So gamma is equals to 0. So this is the final equation. PE is equals to P max sine del. Where P max, what is P max? P max is equals to E1 dash modulus of E1 dash into modulus of E2 dash divided by X1. This is called power angle equation. Until now we had seen power angle equation derivation. This equation is called power angle equation, and when we plot the graph between the P and the del, this is the power angle curve. This is the power angle curve. Now if you see the power angle curve, as del increased beyond 90 degree, that is after this region, PE is decreases. When del is reaching 180 degree, PE will become 0. Beyond 180 degree, actually after 180, how you will get? This is 0 to 180, and beyond 180 will be getting a negative graph like this. This is 0 to 180, and beyond 180 will get a negative. Here we had 180. So beyond 180, PE becomes negative, which implies power flow direction is reversed. When PE is positive, power is actually given to the grid. That is from, this is the motor, if you see here, this is the motor, and suppose this is the infinite grid. Then power will be given to the grid when PE is positive. When PE is negative, whenever power will be given to grid, you know, generator will be producing the real power to the grid. So when PE is positive, that is from del is 0 to 180 degree, power is given to the grid. When del exceeds 180 degree, PE will become negative and power is taken from the grid. Power is taken from the grid means it acts as a synchronous motor. So for 0 to 180 degree, it acts as a synchronous generator, and for greater than 180 degree, it acts as a synchronous motor. The maximum steady state power transfer will occur at del is equals to 90 degree. That is PE max. This is called as pull out or steady state limit. As I had said here, this is the P max. The actual practice of del will be kept around near 30 degrees. So now we had understood what is the steady state stability limit. Steady state stability limit or pull out limit is the maximum steady state power transferred. That is, when in this equation, when del is equals to 90, that is PE is equals to P max, which is equals to E1 dash E2 dash by X12, or E dash into V. You can take E dash into V by X1. Now, the stability limit is the maximum power that can be transferred in a network between source and the load without losing synchronism. So that is the maximum power, that is this peak. This peak, this is the P max. This is the maximum power at which the without losing synchronism, the steady state which can be obtained without losing synchronism. Now, methods of improving the steady state stability limit. We know steady state stability limit is, what is steady state stability limit? E dash, that is the P max, modulus of E dash into modulus of V divided by X. X is the transfer reactance. So if you want to improve the steady state limit, one thing is we can operate at high voltages, then we can reduce, that is by increasing numerator or by decreasing denominator. By increasing numerator means we should operate the system at high voltages. If you want to reduce the denominator, you should reduce the net reactance of the system by using parallel lines, midpoint compensation, series capacitors, double circuits, and bundle conductors. The next topic is swing equation, that is dynamics. So with this, I stop this video. Thank you.